Go ahead.
So in the last class where we found out the temperature.
Yeah.
The temperature should depend on m square minus q square. So the temperature was, in the numerator it was under root of m square minus q square. So now the point that if, for example, m goes equal
In the numerator.
Yeah. So if m goes equal to q, for
Yeah.
example, some
Yeah.
units to carry,
Yeah.
this means that the temperature is
Zero. Yeah.
What does that mean?
It means, so those are called extremal black holes. And yeah, I mean, they're a specific kind of black hole. I mean, generally speaking, one can think of them as certain purposes, at least from the point of view of, let's say, string theory or something. Especially if they have, many black holes which are easy to study in string theory are what are called supersymmetric black holes, and they are all extremal. So that means that they are zero temperature black holes, and they're, it's just from the point of view that we are talking about right now, they are kind of like, in some sense, they can be thought of as ground states of certain theories or some subsectors of the theory and so on. Okay, so, but yeah, I mean, from our perspective, it just happens to be zero temperature, that's it. So we don't really care so much at the moment, yeah. Yeah, that's right. Well, I mean, information paradox, and depend on what you mean by the information paradox. They can still have entropy. So there was a while, I think, in the history of the subject that people were debating the question of whether zero temperature black holes have entropy. But it turns out that it is very natural that they have entropy because, they can have finite radii, right? So even finite temperature, zero temperature black holes can have areas. So if you have an area, then it's natural to attribute entropy to it. And if you do that, it turns out that, for instance, in string theory, you can compute. You can explicitly show where that entropy comes from. So in that sense, yeah, so the information paradox in the, in the entropy sense, but typically what one means by the information paradox is more like the temperature related thing which connects with the actual dynamical evolution of the black hole. So in that sense, yes, I mean, maybe that's not quite information paradox, but understanding the micro states of the theory is also a question that is not accessible in general relativity, right? But that's also a problem. So that problem, how you access it, is related to, again, this question. So that question is still very much valid for extremal black holes. At least if extremal black holes are stable. So there is also, not all extremal, there is this Nernst theorem type of ideas, right? Nernst argument is basically that you cannot bring an object at zero temperature by any finite sequence of operations. So something analogous to that is actually true even for extremal black holes. So you don't expect to be able to reach zero temperature by any normal physical process. Except, but on the other hand, the zero temperature supersymmetric black holes are in some sense kind of like, as I said, they have properties of degenerate ground states. Degenerate means they're highly degenerate ground states, that's why they have entropy. Okay, so in that sense, those black holes are interesting, but it may not be the case that non-supersymmetric extremal black holes may not be very physical. Okay, so yeah, there are many things one can say here, and there is a lot of work on extremal black holes because they are quite accessible, at least in some cases, from string theory. So for instance, as I said, entropy is one problem, and information paradox is another problem. So that's the way I presented in my first lecture. So from that point of view, the entropy problem is accessible and solvable in some cases for supersymmetric black holes in string theory. So this is what was done by Schrodinger and Waffa in 1990s. Okay, so yeah, any other question? It just means that, like in the thermal field theory, you have so the reason why we did that is because first I told you that thermal periodicity basically means in standard quantum systems that there is a periodicity in the Euclidean direction can be interpreted as temperature. So this is my first statement. Then I noticed that there is a natural reason to associate a periodicity for black holes if you continue them to Euclidean signature. So this was the second observation. Together we make the claim that black holes have a temperature. So the first statement is that periodicity in the Euclidean direction is an indicator of temperature, first observation. And the second observation is that there is a good reason by demanding this smoothness at the tip that black holes have temperature, because that naturally leads to a periodicity. So those are the two things. So anything else? Yeah. Sorry, which what? Yes.
Are they eternally existing without no mass in space? Because inner results themselves are not stable.
inner horizon stability is not necessarily accessible to outside guys, right? So if you are standing outside of a black hole, inner horizon is, as far as we are considered, they are kind of a fictitious entity. You know, from our perspective, if you're an outsider, if you're standing at the asymptotic region of space-time, inner horizon is just a fiction. So the stability of a black hole is, you know, it depends on what you mean by the stability of a black hole. So if you're talking about, you know, there is perturbative stability, which is what you're talking about, of the inner horizon. But for instance, in the case of Hawking radiation, for instance, there is, you know, let's say you have a Schwarzschild black hole. There is no perturbative instability. But at the same time, the black hole is unstable because it Hawking radiates and evaporates away eventually. Right, so that kind of question is where whether the black hole is stable or unstable is what I meant when I was talking about extremal black hole. So a Riesner Nordstrom black hole, if they have finite temperature, they will always radiate. All black holes which are at finite temperature are fundamentally unstable because of Hawking radiation.
So whatever happens to the inner horizon not affect external horizon radiation?
Well, I mean, these are so without understanding really what the inner horizon is, we can't really make these statements, right? Inner horizon is an unstable region, and so there is good reason to think that if you perturb the black hole, you know, even slightly, even fluctuations which are small at the outer horizon will diverge at the inner horizon, and because of that there will be instability. So in that sense, I mean, it's like if you really wanted to think of a charged black hole, it may be more appropriate to think of, if it is a physical object, probably you will have a singularity at the inner horizon. That's probably more natural. So there is, you know, but I don't think these things have fully been pursued to the completion. So, but generally people believe this. Yeah. So was there any other question? One more question I'll take before going. Yeah.
So the metric that you defined after Euclideanization of the
yeah.
Yeah. So you said that there is no singularity in that metric, there is rho squared e5 squared plus 0 squared. So what do you mean by that? Because at rho equal to 0, the metric will not be defined, right?
You can think of it as a chart in flat space, right? I mean that singularity you can also see in just, you know, this. If you write it like this for Euclidean metric in flat space, okay? So this also looks like singular at rho equal to 0, but we know that we can cover it with another chart and it's fine. And then you can write down a coordinate transformation. So, but that is not possible if phi is not phi plus 2 pi. If this is not the case, if this number is different, no chart will fix that for you, because there is a conical defect at the tip. Okay, so that's what I meant by the statement that you are choosing this periodicity so that it is regular. So yeah, I think we have to cover some new territory. So if you have questions, you can ask me, you know, email. Email is the best way to catch me. Okay, so it's also the best way for me to avoid you, but I'll try not to. So, okay, so today what we want to do is, so I was thinking actually that what is the best way to talk about computing, you know, this thermal aspects of black holes. And I think the old school way of doing it is sort of to compute, let's say, quantum field theory in the background of, let's say, Rindler space or black hole, Schwarzschild black hole. And I think we may touch upon it and maybe discuss it in various ways. In a very, you know, in the way people typically do is you take a scalar field in the background of black hole or Rindler space, quantize it in modes, just like in standard field theory, and try to do various things. And so this is certainly a viable way to go about it. But I think that, and we may do it, we may do at least parts of it. But I think that a more powerful way of thinking about these things is in terms of path integrals. So I think that's where we will start. So, and if the course requires it, I'll kind of go back to this slightly older way of doing things. And I know from talking to Justin that in general relativity course that he has taught, he has already covered, I think, Unruh effect. So if you have not seen it, it doesn't matter. I will, you know, anyway cover it in some way or the other because we need it for sure. But if you take a general relativity course, I think he does cover quantization of modes in Rindler space and how to get temperature out of it. He does that in his course. And I think the course is going on in parallel, so you will see it at the end. So maybe I'll do it that way as well, because probably for some things I may need it. But right now I'm planning to go in a more, you know, sort of more intuitive and maybe slightly less familiar way of looking at this, because I think that the path integral approach to these things is, you know, I think it is of great pragmatic use, even though the path integral itself is not a very well defined object. Okay, so the first observation is that, so what we'll do today is we'll just talk about how to use path integrals to define states in the Hilbert space. Okay, so path integrals, if you have not seen, how many of you have seen path integrals? How many of you have not seen path integrals at all? Not seen path integrals at all? Nobody. That's fantastic. So that's great. So if you have seen path integrals in the context of harmonic oscillator, that's good enough for my purpose anyway. I mean, even that I don't need. If you take at face value a few things that I'll say in the beginning, I think this is more than enough. Because anyway, a path integral is a formal object. They might tell you that it is a thing that you can actually do, but except for the harmonic oscillator, most of the path integrals that you're seeing you're just believing things for free field theory by analogy. Okay, but most of the time the path integrals that we are interested in, they are formal objects, but they are so powerful that many times you can get great, excellent answers at the end, even though you don't know what you're talking about. So that's what is great about path integrals. So the first observation is that quantum field theory is often or very conveniently defined in Euclidean signature. So this already we saw a bit of that yesterday because we talked about thermal field theory. So this is just happens to be the case because correlation functions are typically better defined in Euclidean signature for many theories. And the reason is fundamentally very simple because in Schrodinger equation, if you like, is a diffusive equation if you are working with Euclidean time. But if it's an oscillatory equation if you work with Lorentzian time. So this means that so for many purposes, if you have oscillatory wave functions, as you will see in a second, for path integrals that we define, they don't damp very well. So we are going to define integrals which involve these fluctuating phases, and these fluctuating phases will not converge very well if you are in Lorentzian signature. So this is sort of the zeroth order observation, and so what we want to do is but QFT is very well defined in Euclidean signature. Okay, and they only have, so one other interesting point is that if you have seen field theory, in field theory one of the key objects that we often study are, let's say, things of this nature. Okay, phi 1, phi 2, let me call it T1, X1, T2, X2, etc. with many insertions of this type. So so this is the kind of object that we typically study in quantum field theory. Okay, so this is what is called a correlation function or an endpoint function. Okay, so this guy is, if you know all the correlation functions of all the operators of in a field theory, then we have solved the theory. Okay, because from that we can reconstruct, if you want, all the full eigenspectrum, etc., etc. Typically this is never possible, but the question is whether we can solve it in some approximation at least so that we can extract the information that we want. Okay, so the key point about Euclidean quantum field theory is that correlation functions of this type are extremely well defined except when these points coincide. So the only kind of singularities that you have in a Euclidean quantum field theory are what are called coincidence singularities. And this is essentially what makes Euclidean. So the only thing that happens is that if you put two fields on top of each other, then you might get divergences. Those are typically what are called short distance divergences in quantum field theory. But the thing is, those are essentially the only kind of divergence that you have in Euclidean field theory, but that is not the case in Lorentzian signature. And you can sort of see that because let's work with, let me assume some translation invariance so that I can move one of the fields to this. Okay, so I'm moving it, let me call it phi. So this is basically going to be a function of tau and x. Okay, or t and x. Okay, so right now I'm not specifying whether the t is Euclidean or Lorentzian. Okay, so the claim is that in Euclidean signature, only when t equal to 0 and x equal to 0, you will have singularities. Okay, that's the only time when you will have singularities for this guy. But you can, so the point is that these guys are functions of, if you have a Lorentz invariant or a Euclidean invariant, if you rotate to Euclidean signature, Lorentz invariance becomes, usual rotation or translation invariance, right? So that means that this is even more constrained. What you really have is that this is what it is really a function of. Okay? Because of Euclidean invariance. So you have rotation invariance and translation invariance, and then just based on the symmetry of the theory, if you claim that this theory has Euclidean invariance coming from the Wick rotation, once you rotate from Lorentzian signature to Euclidean signature, you will basically have full rotation invariance in T and X. So so this is what you have, right? So this function it can have singularities basically only when T and X are 0. This is the claim. Okay, and that's a property of quantum field theory. So quantum field theory has a property that when two fields coincide, two operators coincide, they can have divergences. Okay, so these are called short distance divergences. So, but it is coming from this kind of a structure. So what happens when you do Lorentzian signature or analytic continuation to Lorentzian signature is that this guy now becomes a function of this form. Okay, because you are going from T to minus IT, right? So, and you can see that the coincident singularities, which was at T square plus X square equal to 0, was the place where you had singularities before. That's when the 2 points coincided. So the corresponding point here is no longer a point, instead it's a light cone. Yeah. So that is basically coming from the fact that there is this field theories. I'm assuming that the field theory has a symmetry under rotations as well as translations. So the only invariant you can construct out of Tx, if you wanted to really be more this thing, you can write it like this. This is phi, and this is phi T2x2. Then it's an exercise if you like. Exercise that this will be, if you want it to be Lorentz invariant, it has to necessarily be, or Euclidean invariant, it has to necessarily be a function of these two guys. This is the only thing that you can write. First of all, the translation fixes only differences. It fixes it to differences, and rotational invariance in the full xt Euclidean space fixes it to be just a function of this guy. So that's the way you can make it very systematic. You can write down, if you want, the symmetry generators of the theory. Let's say you are working with, very explicitly, if you want to work with simple case like free field theory, you can write down the rotational generators of free field theory, etc. But it's kind of intuitive also. You know what I'm saying? But it can be made extremely systematic, and it doesn't depend on even the free field theory assumption or anything. You can show it even in general. Okay? So this is what you get just from the symmetries of the underlying assumption about the symmetries of the theory. Okay? And if you make that assumption, the claim is that once you Wick rotate, your dependence on the function will basically go to this. And now the analog of this guy, this coincident singularities, once you Wick rotate, they basically what you get is what are called light cone singularities. Okay? So this is a feature of quantum field theory, and the reason why I said that is because a lot of the time quantum field theories are defined by starting from Euclidean signature. In fact, many of the Lorentzian statements which are not so transparent become much more intuitive and easy to understand when you start from the original Euclidean signature. For instance, CPT theorem is a trivial fact about how if you flip signs of axes in Euclidean signature, some flips of signs of axes can be understood as rotations. So if you have a rotation invariant theory, then in Euclidean signature, it necessarily has to be CPT invariant in Euclidean signature. So CPT invariance, but once you rotate it back to Lorentzian signature, it's a bit less transparent why this has to be true, but that essentially arises because of the fact that in Euclidean signature, some flips of coordinates. Let's say if you flip two coordinates in some, let's say in 1+1 dimensions, then it turns out that you can understand it in terms of a rotation. So some flips of coordinates can be understood in terms of rotations is essentially the reason why rotational invariant theories have to necessarily also be CPT invariant. Okay, so that's how CPT invariance is. The easiest proof of CPT invariance is in Euclidean signature. Okay, so that's just a fact about Euclidean field theories, and the reason why I mentioned that is because that's where we are going to start our path integrals. So we are going to start our path integrals in Euclidean signature, and so the basic statement is that, so I'll just write down a formal object for you, and I will claim that. So essentially the point is that this is what you will be interested in. So you're interested in transition amplitudes in Euclidean space. Okay, let's say I will define what these things are. I'll spend some time talking about what these Kets and Bras are. But let's assume that, like if you want to make it a little bit, first let's make it in quantum mechanics. Okay, so you can think of this, if you like, as a harmonic oscillator. Okay, so the claim is that this can be written as is equal to x2, and you have some formal measure, and then you have some action which is a functional of this x. Okay, so this is what essentially defines the defines a path integral. Okay, so you can think of it as a formal object, but the utility of the formal object is that it works very well. Okay, so with some basic intuition and being careful in various places, it's a formal object, but we understand physics well enough that we can do many very concrete calculations with it. Okay, so this measure, so in the case of the harmonic oscillator, this measure can be made completely explicit, and this is what you may have learned in some courses. But in the cases that are of interest to us, anyway, the measure is not defined, or in most cases it's not even calculable. So even formal expressions cannot be written out in many cases. So that means that this expression is you are only going to get an illusion that you understood path integrals if you didn't have a course on path integrals. It's completely fine, because this object is anyway formal. Okay, so this is what this is the statement. So first let's write down this object on the left hand side. Except for the fact that it is a Euclidean signature, I'm sure you have seen, right? This is basically just a standard. You can think of it as a harmonic oscillator, and this action is the harmonic oscillator action. Okay, so harmonic oscillator Hamiltonian, how to go to action. That's how I'll leave as an exercise. Okay, so you can write it as a time integral. Okay, so this I'm sure you have seen. So, and completely by analogy, I'm just going to define a Euclidean path integral for a field. Let's for convenience, I'll think of it as a scalar field, but it's not important at all. So this tau is some final time. So I'll explain these things a little bit more. So phi 2, and you have d phi, which is some measure, and then you have Euclidean action for your scalar. Okay, so the claim is that what you have to do in order to compute a transition amplitude is basically sum over every possible trajectory or field history between some initial configuration which is specified by your x1 or phi 1 here. So this object maybe require a bit of an explanation. I'll spend a little bit of time explaining this, because this guy is usually not as, like you might have seen discussions of field theory in the number basis, which is where the Fock space is usually taken. But I'm writing it in the field basis. So, but the analogy is with this here, it should be clearer. So instead of working with an n basis, which is what you usually always have in quantum field theory, I'm working with the analog of a position basis, which is what this is. Okay, but I'll say a bit more about that. But so for making the statement about what this is saying, it's basically you integrate over every possible field history or variable history. If this is in the case of here, it is x is the variable. So the history of that variable, you integrate over every possible thing weighted by the action of that history. Okay, e to the minus action of that history. So this is what basically gives you this transition amplitude. So this is what essentially defines a transition amplitude, and this is a Euclidean evolution. This is some measure, which is usually like you'll have to, in some cases this measure is important, but oftentimes we don't really need it, so we can get away with it. And I'll draw a picture for this. I'll draw a picture for this, which is oftentimes convenient, which is that you have, so this phi 1 is so this is the time direction. The tau is increasing upward, and this is what I call. So, and the integral is basically done in this geometry. So where I'm assuming that I'm integrating it in some space-time. Okay, some Euclidean space-time. Here it is. Looks like it is standard Euclidean R. Let's say RD minus 1 or R2 or R1 here. Okay, here is just one line, and then there is a time direction. Okay, so it doesn't have to be R1. It can be any manifold. So this definition is perfectly well defined. Okay, so this is what I mean by my quantity. So this phi, so this is the only piece that requires a real. So if you are familiar with the left hand side in the harmonic oscillator case, the only thing that you really need in order to go to generalize to here is that what is this ket phi? Okay, what does this ket phi mean, and what does that have to do with the phi 2 and phi 1 I wrote here, right? I'm basically integrating it. So what this phi 2 and phi 1 are basically field configurations. Note that the path integral is a completely classical object in some sense. Every variable inside here, there's no operators inside. Okay, it's all integration over standard real variables, or sometimes Grassmann variables if there are fermions and all that. But it's basically a completely classical integral. So this guy is basically just saying that the field configuration at the final time is some configuration phi 2. That's what this is saying. Okay, so this is just specifying, this is of course a function of, whatever this x should not be confused with this x. This is some location in space. Let me not put that here because we don't really need it anyway. So this is basically a field configuration on this slice, and the other guy is a field configuration here. So those are just real values. That's all points on that line, on that spatial slice. Okay, so that's that. So this is a completely reasonable integral, assuming you could define this measure, and this integral was doable and so on. None of these are the case, but these are all things which we can at least get behind. So the question is, what is this ket phi, right? So this is basically the analog. So let me write what it stands for. Phi stands for a state in the field basis of Schrodinger representation. So all of these words, yeah.
Kets are not in entire picture, are they?
These are all Schrodinger picture states. So yeah, these are all Schrodinger picture states, and yeah, we will never talk about interaction picture at all because interaction picture is a tool. And I was saying interaction picture is basically just a tool for doing calculations around free theories. So if you're really interested in we are never going to talk about interactive field theories at all in this course at all. And what I mean by that is that if we talk about interaction theories, we will talk about in the language of path integrals. So because we are not interested in computing most of the time, like what S matrices are, such pedestrian things we are not interested in. These are, so we are interested in talking about things which are like this is basically a definition of a theory. This could be an interacting theory, but the interactions will not play a role for us. So we are really doing integration of the whole field. There is no part of it which we approximate as free theory or anything like that. None of that. So, okay. So yeah, so for instance, in these kinds of settings, I mean, that would mean that you have a Hamiltonian which is time dependent, right? So if you have a Hamiltonian which is time dependent, many of the statements that I said are not true, because what I'm talking about are theories which have both either Lorentzian invariance or Euclidean invariance. Once you analytically continue to Euclidean signature. So the claim that I made, if you want to go look up a little bit, is that if you have very mild assumptions about correlation functions in Euclidean space, then you can reconstruct a Lorentzian theory always. This is the claim. Okay, so this is sometimes called the Osterwalder-Schrader reconstruction theorem. It's a very fancy name, but I mean the proof is only for very simple settings and all that, but at least as far as I understand, maybe it is true for more general theory. So that basically says that there are some basic assumptions like the cluster decomposition and there is also this reflection positivity. That's another some Euclidean analog of unitarity. So and a few other assumptions. A few other assumptions like that. Then you can always show that a Euclidean invariant set of correlation functions can always be continued to analytically to Lorentzian invariant correlation functions. So there are like 3 or 4 assumptions. So if those assumptions hold, then you can always do that. But what your question is asking is a situation where those assumptions don't hold. Okay, then there is no real statement. So, okay, so Yeah, so this is what I mean by phi stands for a state in the field representation, field basis of Schrodinger representation. And so the idea is that instead of working with the Fock space in the number basis, so number basis, if you are, if I'm assuming that you are familiar with this kind of thing, so then, like a bunch of creation operators acting on the vacuum, basically giving you a state with various number of oscillators defined by their appropriate quantum numbers, which I'm calling I. Okay, so that's what I mean by a number basis. So this sort of construction this is the construction that people use for Fock spaces. So, but I also want to add that the existence of a Fock space is a luxury that you have in free theory. Okay, so what we are going to assume is that, it's easy to show that there exists a field basis of this type, this ket phi type, when you have a free theory. Free theory means a scalar field theory which has no interactions. Then you can show that. So, but it is natural, and so we will assume that such a basis exists even in the interacting theory. Okay, in interacting theories are, generally speaking, most things are not easy to make formal because of renormalization related issues. So for instance, this number basis, even though we do scattering theory in the number basis and so on, these things are not well defined if you have an interacting theory for real. So the Hilbert space of a true interacting quantum field theory is a quite complicated beast. Okay, so the analog, so instead of working in the Fock spaces in the number basis, Fock space in the number basis, I'm working in the field basis. We work with the field basis. The field basis. So I'll explain that a little bit more. And okay, let me also write the analog. So the SHO, the simple harmonic oscillator analog of this statement is, instead of working with the number basis n, you work with the position basis x. Okay, so the position x is in many ways similar to the field basis, the field configuration phi. Essentially because this phi is the classical variable that you're really thinking of in a field theory. Okay, so this analogy is good to keep in mind because it'll keep you from getting confused. And this change of basis, I'm sure you're familiar with the fact that you can change this basis because this is what so this is what one means by, for example, the Hermite polynomial. Right? This is an eigenbasis or eigenstate of the harmonic oscillator, and the fact that it exists and it's a complete set is proof that you can go from one to the other. Okay? So that's the analogy sort of to keep in mind. So the analogous statement is that we want to go to a basis where phi x is your basis element. Okay? So so the point is that if this is something that typically one doesn't do in quantum field theory, even though I think it's a very instructive thing to do. So what we do in quantum field theory, so there's like a huge step when you go from huge step or a sudden philosophy change that nobody tells you when you start with quantum field theory. Right? When you're talking about quantum mechanics, the way you work is you start with, somebody gives you a Hamiltonian, and then your job in solving the theory is to write down the eigenstates and eigenvalues of the Hamiltonian, and if you are able to do that, you declare victory and you have solved the theory. Okay? Then you can write down arbitrary time evolution, you can compute all correlation functions, etc. But when you go into quantum field theory, suddenly nobody ever talks about wave functions or kets or anything like that of that kind. So, but you can always do that. It's a perfectly valid thing to do, even if the Hamiltonian is a functional. Is a integral over all space. Okay, you can still do that. So, and the idea here is that the analogous operation as what you had in working with the x basis is perfectly natural there as well. So you just have to get used to it. There is nothing more happening here. It is just that, you know, the field, the classical or the variables, the configuration variables of your theory are basically, instead of x, it is basically some phi, but it's indexed by this x, right? So this x is the index that captures all the, you know, phi at each location is now a classical variable or a configuration variable. So what really this stands for is in some sense like a huge list of x's, x1, x2, xn, you know, but it's an infinite number. And the analog of x is phi here, and the analog of the index I of the x is your location in space-time. Was that too fast? It's okay? So
we are going from the discrete basis state to a continuous basis state.
no, that is, so when you're working with you know, quantum mechanics to field theory, it's even more in some sense. So for instance, in the case of the harmonic oscillator, for instance, you could, you know, write down, you know, a basis where the basis was, you know, 1 to n, right, in terms of n. But here you will have such a basis in principle for each point in x, if you like. Okay, so it's like the infinity is already there in quantum mechanics, if you like, because x is a continuous variable. But here there is more than that. So I am saying that each of these continuous variables is labeled by an infinite, you know, a continuum of indices.
So each of the x has basically tower of x basis.
No, the x you should not, you know, I'm just saying that x is analogous to phi. I'm not saying that x is the same thing as phi. I'm saying that, you know, like if you have a field theory, so in quantum mechanics what you have is a classical variable is this guy, and instead what you have here is a variable phi, which is, you know, x comma t. And if you had many of these variables, you will have x going to xi of t, where I is some index, right? And that index doesn't have any geometric significance. In quantum field theory what happens is that this phi is basically, this x is basically an index of this form. But that index has physical significance, which is a location in space-time. Okay? So basically, quantum field theory is a theory of operators which are labeled by points in space-time. So that's what these guys are. Okay? So that's what I'm trying to say. So this, you can, it's better if you want to make the analogy more closer to this, this is the way you can think about it. Okay? Because this x should not be compared to this x, it should be compared to this index. Okay? So that's the sort of the analogy. Okay, so, sorry. Yeah, so this translation, in fact, can be explicitly done for free theories. And if you have not done it, I'll give you some hints, but you know, I can't go through in full detail here. But it's a fairly straightforward generalization of what happens in the harmonic oscillator, except that it has more indices and various other things like that. Okay, so it's a little bit more work to do, and it's largely about not getting confused. That's really all that is about. But so this is the sort of the idea. And free theories is explicitly doable. So if you want to take a look, actually a good reference, which is an unsung reference in quantum field theory. So it's a book by a guy named Hatfield. Okay, so Hatfield has a discussion about what is called the Schrodinger representation of quantum field theories, which I think is I think it is worth doing, and he does it very well. And you will see the parallels and differences. Okay, so it's Brian Hatfield. I think it's that's the book that I studied back in the day. You know, when Schrodinger, not Schrodinger, what is it? Peskin and Schroeder was just had a lot of typos and all that. So this is it's a very good reference. So. Yeah, so what does this mean? This basically means that we are working in a basis where the phi effects, the operator phi effects, let me call this. So this means, so basis is phi effects instead of the number basis. The number basis is what I wrote down as that n guy there. So, okay, so this is, so a tensor product of all of these things is the basis of Fock space. So this is note that, yeah, I mean basically this is the basis of Fock space, and I am saying that I can actually go to this basis if I like. Okay? So, and this means we are working in a basis phi x, the field operator, this is the key point, is diagonal. Okay, so diagonal basically means that you're in the basis where phi of x acting on some ket phi basically gives you phi, and this should be compared with this equation. So all of those symbols mean various different things. Okay, so this is an operator x acting on the ket x, giving you the real value x, again acting on the same x. Okay, so this is the analogy. Okay, so and if you want to make it more similar to that, you can put indices for each of them. Okay, so that's what this is. And this equation, I think it is worth staring at it for a few seconds. So this you should think of, this is the analog of an eigenvalue, right? But note that it is not quite an eigenvalue, it's actually a function, right? Because it is a configuration in space, in a spatial slice. That's what this is, okay? So this is better called really an eigenfunction, but unfortunately we use the word eigenfunction to talk about eigenkets, so I will not do that, okay? So this is basically the eigen, within quotes, value of the field operator phi acting on the ket phi, and this is what defines your ket phi, if you like. Okay, this is just the same way that this guy defines ket x. So the non-trivial bit of information here is that there exists a basis change from n to x in the case of harmonic oscillator, and from the number basis in the field theory to this basis. Okay, and those two are exactly the same calculations, except this has more indices and more bells and whistles. It's exactly the same thing. Okay, so I think, yeah, I'm just, instead of deriving it completely systematically, which will take me a whole class, without really adding any serious value in my opinion, I'm just going to motivate it. Okay, so
the vector sign is still there, right? Or is it
which vector sign?
in the right hand side, the eigenvalue?
Yeah, here that's true. Yeah, you can put this if you want. But I mean, maybe it is okay to just suppress it also. I'm just, I'm not. The only reason I put the vector sign is because this is, in some sense, you can think of it as being defined on one spatial slice as opposed to some random, co-dimension one surface in space-time. This or random, this is not all over space-time. This is more of a Hamiltonian concept. I'm saying it's basically defined at the level of, we are defining a Hilbert space and time evolution. All of this in Schrodinger picture. So that's the reason why I put a vector. Okay, let me put a vector here. But I might not always put it, but it's always understood that these are Schrodinger picture things that happen in some Hilbert space at some particular time. Okay, so these are states in the, suitably defined states. Okay, so and similarly, this guy here is what is called an eigenfunctional. So most of what we are talking about, if you replace function with functional, it will just go through. Functional is just a name for a function, so if you're, when the index was some discrete index, it was kind of convenient. But now, on the other hand, we are going to specify a configuration in all space. Okay, so that's what really, so you have to specify a function in order to talk about, for instance, this ket. Okay, so and that's the reason why that object itself is called a functional. So a general state is described by a ket, which I will call psi, which in the basis phi is represented by a wave functional. Okay, so this is the exactly analogous statements I'm sure you're familiar with. If you have a standard wave function in quantum mechanics and your basis is x basis, psi of x is this guy, x, this thing. So the only thing is that, like the square bracket means that this is not some this is basically, if you want to be mathematically precise, this is a map that takes, this a field, a function to a complex number. So that's what this psi is. Okay, so it's not taking some real value like x to the complex number. It's taking a configuration, a field configuration, or a function to a complex number. Okay, so again the analog. So let me just write it. Psi of x is this guy. Okay, so this is our sort of picture. Okay, so just to give you a sense that this is not completely, abstract, I just want to write the Schrodinger equation, the conventional Schrodinger equation. If you were to follow the path that we would take in standard quantum mechanics to write down free theories. So you had a free scalar field theory, and so this is what you would write. Okay, you don't have to really. I'm just writing it to see the motivational purposes only. It's not so much that, but you can make it very systematic though. Okay, so but the analogy is sort of should be clear, right? So now instead of delta by d by dx, you have a functional derivative with respect to phi, which basically defines your canonical momentum in field space. And then you have, this is basically the sort of like the mass term, or the omega square x square type of term, which comes from the non-time time derivative parts of the Lagrangian. Okay, so this is what the structure would look like, and you can see that if the Hamiltonian, the second and third terms don't have any explicit time dependence. So this also means that you can write a basis. Or you can also go to a time-independent Schrodinger equation by looking for things of this nature. Okay? So this is also entirely possible. So now if you plug it in, you will basically be able to write down time-independent Schrodinger equation and then solve it, and you will get a functional. And in fact, the ground state, in all the states, in the case of free theory, you can write the entire spectrum of the theory in this language. Okay? And it will basically look like a Gaussian integral, the ground state. Okay, so so that's the so that's the structure of this theory, and you can look at Hatfield. Hatfield has a nice discussion of it. Okay, so so and typically, however, for historical reasons, we have generally worked with this basis where the number is fundamental, and part of the reason is it's not just historical accident, it's partly also because we define particles and in terms of momentum eigenstates, and momentum eigenstates make sense in Lorentz invariant quantum field theory because translations are a symmetry. So momentum eigenstates make sense asymptotically, so if you want to compute, for instance, scattering amplitudes, that's a good basis to work with. Position, on the other hand, is not a conserved quantity, so it's not interesting to define eigenstates of position in a Lorentz invariant theory. It's not very useful. So that's the reason why people work with it, but I want to emphasize that the technology is completely parallel and it works. There is no even really technical complication either. Okay? So the free theory, the only complications are ultimately coming from the fact that interacting field theories are hard. And that's hard even in the number representation or any perturbation theory. So there you'll have to again arrange your perturbation theory accordingly, but the formalism is actually equally sound in Schrodinger representation as well as in this number representation. Okay, so both are equally well defined. So so of course this discussion I phrased it in sometimes in the language of free theory, but this idea that there exists a ket phi which is useful for defining configurations in field space is more general. We expect it to be more general, and we'll assume it to be so. Okay, so that's what we are going to do. This, yes, here it is Lorentzian time, that is correct, because this I is sitting here, right? So here I'm just writing the analogy with standard, free quantum field theory, let's say in the first chapters of Chethan. So this I is definitely there for that purpose, but it's not important. If you can Wick rotate it, and then you will get a, a diffusive type of Schrodinger equation. So that's also fine. Any questions? Okay, so now I think we have enough sort of cultural familiarity with what we are going to do. So yeah, so this means that, you know, I wrote down an object of this form, right? This is what I wrote down. So I wrote this down as a path integral. So now I can make it slightly more abstract. Let's say I can call this guy to be a ket of this type. Okay? And I can say that this stands for the integral where I integrate from phi at t equal to 0 to be some phi 1, and e to the minus s of phi is my integral, and I leave the upper cut. You know, if I draw my picture here, okay, so this is at t equal to t1, it's t equal to t1 or t equal to t, let's say. So this is tau equal to 0, time is going this way, and yeah, so this is what I had, right? So the claim is that this stands for phi 1. So at tau equal to 0, I specified my field configuration to be phi 1. That's the analog. So note that this phi 1 is a field configuration. It's a classical field configuration. Okay? So, and that is the analog of saying that the position of the particle at some initial time was x. So I have to specify an entire field configuration to specify that, something of the kind. And once I have that, the claim is that I can make it a more formal tool. So if you really wanted to do this integral, and assuming it was doable, I'll have to specify the boundary conditions here as well, right? But the statement is that I'm going to call this ket, you know, this e to the minus 2h, you know, acting on the ket phi 1. I'm going to formally think of it as a path integral where the lower part of the cut is specified, lower part of this integral is specified, but the upper end I'm not specifying. So here I'm not specifying what the field is. This is in some sense, so you should think of this as this is what stands for a ket in the path integral language.
Even though the right hand side is fully classical.
So it's fully classical in sort of a fictitious way, right? When you say that it is fully classical, it is accessing configurations which are not classically well defined. What it means to say classical is just that these are C numbers. That's what it means by classical here. So, but you are still integrating over configurations which are not allowed by classical equations of motion. So this is this integral is all over, you know, all the phi's are real numbers or Grassmann numbers, depending on if you have fermions. But otherwise, that integral itself is it can scan physically, I mean, classically not allowed configurations, right? So that's the reason why the path integral knows about the full Hilbert space. So there is no Hilbert space showing on the right hand side, but it knows about Schrodinger evolution, gets all of that implicitly. So the fundamental reason why the path integral is a useful object is because ultimately, you know, in field theory or in quantum mechanics or in quantum field theory, we are interested in correlation functions. And correlation functions are basically just complex numbers. So that those integrals will basically give you some complex number, as long as you can make them well defined. So in the final stage of quantum mechanics, we really don't need kets or bras. So we only need correlation functions, which are basically amplitudes. Okay? So to compute an amplitude, a path integral is good enough. But to specify states and operators, you know, you have to do some trickery like this. So because if I integrate it like this and leave this part unspecified, that's my way of thinking about a ket in the path integral language. Okay, so any other questions? Plus del square, this one? No. There is basically the point is that this is what becomes sort of the canonical momentum, right? Just like in the case of maybe there's a minus I here, but still the overall sign will be minus. Okay, so this sign is questionable. I think it is minus actually, but so this is the canonical momentum in the field space. So, and this guy, it's square. This is basically just the analog of minus, you know, the grade square in spatial, this thing. So note that all the x dependence, etc., that come up here, they don't play any role. They are just like potential terms from this functional point of view. So they don't really matter. So this is the guy that really tells you that the canonical momentum in field space, in the functional language is basically that. So that's why there is a minus sign. Okay, so in this language, so once you make this definition, my original path integral where I specified a phi 1 here just becomes, this, or phi 2 here, sorry. So if I specify a phi 2 here, it will basically become this. So this integral, but on the other hand, is understood sort of formally without specifying what the boundary conditions are here. Okay? So that's really what I mean by a ket in the mathematical language. So now we come to the most sort of one of the useful things that we can do with this kind of formal tool. So that's essentially, we have already done it. What we are doing here is what is called a cutting a path integral. A cutting a path integral basically means that you're looking at, let's say, codimension 1. Codimension 1 means it's one less dimension than the total dimension, okay, of the space. So codimension 1 slices in this space-time that you're working with. Note that I'm not really restricting myself to 1 plus 1 dimensional space-time. This can be any dimension. This is time, so this has single dimension, but this can be any dimension, it doesn't matter. So that means that when I slice the path integral open, I'm always assuming that I'm doing it in a codimension 1 surface. Okay? Where in principle I can specify a field configuration and compute an expectation value. So this is the idea. So let me write it, kind of make it formal. A cut is a spatial slice of the Euclidean manifold. Note that we are always whenever I talked about path integrals, I have so far been talking about Euclidean path integrals. Okay? So, how are we doing on time? Oh, it's already 12. Okay. So, and this is it's a codimension 1 surface. So let me use the word codimension so you're not scared of it. Codimension 1 surface. Codimension 1 just basically means it's one less dimension than the total space-time dimension of the manifold. Okay, so so what we have done so far is we have taken some space-time and put two cuts, one cut here and one cut here, and then computed our. So this is not a boundary. This is just you can go off to infinity if you like. So whatever is the space-time, I'm putting some cut here and some cut here, and then I'm evolving it and computing it. Okay, so that's the picture. Yeah.
The exponential of minus tau, which this is basically the unitary evolution of it.
It's not unitary. It's a dissipative evolution in Euclidean space, but yeah, it's coming from a unitary evolution in Lorentzian signature.
Yes, then this object is
that depends on what you're doing. So if, for instance, S matrix, you have to have, like, for instance, asymptotic free states and various questions like that. So it's a correlation function. And S matrix, it's more correct to say that an S matrix is a correlation function rather than to say that this is a S matrix element. Because if you don't have, for instance, you don't need to have an S matrix in a theory for correlation functions to make sense. So this is just some Euclidean correlation function of a general theory, and that's what we are computing. Okay, so this, so one more comment make here is that typically, so note that the way I define these things, it's not, in Euclidean signature, because there is no signature that picks out the time direction for you, it's not very clear what you mean by time. Okay, so what we typically do is that we assume that there is some translation freedom, there is, let's say that so the direction, so let me just write what I say instead of, typically we consider Euclidean spaces where the tau translation is a symmetry of the theory. So this might be so the reason is that in general, if you have a Euclidean manifold, Euclidean space with Euclidean signature, there is nothing that picks out what is time versus what is space, right? So, and in principle, you could do the path integral any way you want, and there is nothing that really, there is this integral. Here I told you, here what this means is really that I'm assuming that my Euclidean signature metric has a translation freedom in some direction. And that direction is what I'm calling my time direction. Is that clear? So it's very important that that is the case, because otherwise you will get various ambiguities. The path integral itself may be more well defined, and maybe it is telling us that we should have better understanding of the path integral. But at least in order to make sense of it immediately, in terms of Lorentzian theories by analytic continuation, we do need some time direction in the Euclidean signature, which has a translation invariance. So I'll give you an example to make it a little bit less abstract. So this means that, so this is necessary if you want to Vic-rotate and interpret that as a true time direction. So let me say what I mean. I'll give you two examples. So the Hamiltonian of the theory is basically the generator of those translations, those tau translations. So that's the understanding. And the reason why this is interesting or useful is because so let me give you two examples of what I mean. So maybe the example will make it more clear. So Euclidean space. So there are two ways in which people will use the word Euclidean space. So Euclidean space sometimes means things where there is no Lorentzian signature component of the metric. But another and sort of old, not just old. It's another use of the word Euclidean space is when you say that it is, it is Rn with a Euclidean metric. Euclidean flat metric. So those are two uses of the word Euclidean space, and you'll have to kind of figure out what the context is. So when I'm talking about Euclidean space now, I'm talking about Rn. So far in all the discussions, I was always talking about Euclidean signature, but that's just any metric with all positive, signature. So here, what I mean, let me again draw a picture, sort of a simple picture of Euclidean space. And if I go from here to here by Lorentzian thing, I'll have a t here, and the time is flowing this way, or etc. And this is x. Okay, so this is what you typically expect, and this is trivial, right? You have a Euclidean plane. So, but you could also do a similar thing by starting with. So, and here the understanding is that the theory has time translation invariance here, or in the Rn case, it has the full Poincare translations, right? Poincare transformation worth of freedom. So time translation is just one of them. So, but you don't need full time translation, full Poincare transformations. What you really need in some cases, let's say that you have a theory where your time direction is, you choose it to be tau, and you have some angle direction which I'm calling phi, not to be confused with the field phi. Okay, so this is an angular guy, and then you again do this, and then you can basically kind of think of it as a cylinder here, right? Let's say you have a, if you have not seen it, I don't know how transparent this will be, but those who have seen a little bit of conformal field theory will see that. So here, so what we did here is that we took our Euclidean theory to be defined by a tau translation which was radial. Okay, and if you take a time direction, so what we essentially did, you can, in terms of path integrals, you can think of it as a quantization process. Okay, essentially I gave you a prescription for defining some correlation functions in some quantum field theory. Okay, so, and the point is that this, so if I didn't tell you what my time directions were. I just told you some Euclidean time direction existed, and I drew a picture. But I could do the same thing with a radial direction here, and with the other directions being some phi, etc., etc. And as long as this time translation in the radial direction is a symmetry of the theory. Okay, so if let's say that there is some field theory which has time translation on the radial direction, which is a symmetry in Euclidean space, such theories are called scale invariant theories. So scale invariant theories, you can actually do this kind of a translation, this kind of a Vic rotation to Lorentzian signature, and then you will get theories that live on cylinders. Okay, naturally live on cylinders. And this is something in the context of conformal field theory, this process is called radial quantization. Okay, so radial quantization is the idea that, and note that it was crucial that the theory had a symmetry under these radial movements. Okay, I'm calling that radial movement tau to build the analogy with my path integral more transparent. But the point is that the fact that the theory has a symmetry, if I move in this direction, is what enabled me to do this. Okay, so in Euclidean path integrals are perfectly well defined as long as I have a translation freedom or a symmetry in some direction and in some direction of space-time, and once I have that, I can quantize the theory using my path integrals the way I did. Okay, so this is what enables you to do what is called radial quantization in the scale invariant or conformally invariant theories. And once you do that, you can do this Wick rotation and go this way.
So why do you call it scale invariant?
Because this movement in the radial direction has an interpretation of scale invariance in the theory. So from what I said, well, I mean, you can think of it as because that's essentially the definition of scale invariance, if you want. I haven't told you, I mean, if you see an example, it'll become more clear, but for instance, you don't have to worry about what the scale is here right away. But what I'm trying to tell you is that the choice of the Euclidean time direction on which you are cutting your path integral, like I was saying there, is really dependent only on the symmetries of the theory for pragmatic purposes. It might even be more general. It's not clear that you should only do these things along, constant, on slices where the t direction is constant. It's not completely clear. The path integral, at least from the right-hand side of these pictures that I drew, it looks like the path integral should be completely well defined, even if I just put randomly. Like, okay, there's some space-time sitting here, okay, and I just did my path integral. This is some tau and this is some x, let's say. And I just did my path integral with fields that are arbitrary here and some field I specified here. Okay, this is in principle a perfectly valid object if you want to do a path integral. But its interpretation in the Hamiltonian setting or in the context of in the context of Lorentzian theory is less clear. Because if you have a time translation on the other hand, foliations of that time translation, and I mean time translation in the sense that there exists a translation symmetry in the Euclidean signature, that's all I mean. So if you have a translation invariant in the Euclidean direction, then foliations of that translation, I can put useful data for the Hilbert space there. That's what is really happening when I'm foliating it either this way in this case or in this way in this case. Okay, so this is so that's sort of the quick take on radial quantization, because that's one place where this picture is very, very useful, because radial quantization is really it's extremely natural from a path integral point of view. If you have seen conformal field theory, that's if you're planning to see conformal field theory, that's important to know why it is that people do this.
This thing changes the domain of the spatial coordinate.
Sorry? Sure, yeah. So this is, I didn't say anything about where the spatial slices, in fact I told you that the spatial slices, I'm not specifying what they are, right? The spatial slices can be anything, for example. So I can, I could do this here. I can just take the spatial slices to be a circle here, and that's what I'm doing, okay? And so I'll do a couple of more pictures, and then I think it's already 12:10, so yeah, maybe I can just take a few questions, and I don't think I have time to start a new thing. Okay.
So this tau coordinate,
Yeah.
basically rotating to imaginary imaginary time axis, and these cylinders are basically shooting towards us.
Right. Yeah. So basically. So I mean, it's not like I could have drawn the picture actually in the plane, as a radial direction in the plane as well, but it's more conventional to draw it this way for scale invariant theories. Yeah. So that's a statement basically about the existence of that symmetry. So the fact that there is a scale invariance in the theory is what allows me to do that. Maybe I can just finish like couple of more pictures, and then we can call it a day. So it's only 2 pictures. I'll just draw 2 pictures, and since I already mentioned cutting the path integral. Okay. Yeah, so let's talk about what is called. So this thing that I said can immediately be used to talk about what is called the no boundary wave function. And this comes in not just in the context of black holes like we are interested in this course, but also in the context of what is called quantum cosmology. Okay, so the no boundary wave function is something that was originally proposed by Hartle and Hawking in the context of how the Big Bang, what is a good model for a Big Bang, etc. So, but we will need it for other purposes. So, and the idea is more general. So, the idea is just that instead of considering, so in all these cases that I told you, I was looking at space-times where there is a beginning part, an ending part, I put some field here, or a configuration here if you like, which is the same thing as a ket, and another one here. Or I did not specify, then it became a ket. Right? If I did not specify anything here, it becomes a ket, assuming that the time evolution is this direction. Okay? So, but in principle, I can consider manifolds which don't have these lower boundaries. So for instance, I could consider manifolds of this type. Some hole, etc. I don't care what there is in the manifold. You can have multiple holes, all of that kind of thing. So let's say there is a manifold and I specify, this is defined to be this guy. A path integral where there is no place where I'm putting any boundary condition in the path boundary, but it's just a closed manifold of this kind. Okay, and I just integrate over all possible field configurations on this without saying anything about what happens to the lower boundary. And this kind of a definition of a state here on this slice, this is, let me call it sigma, is basically what is called a no boundary wave function. So one of the proposals of Hartle and Hawking basically suggested that the universe originated, the Big Bang should really be viewed as a state which had no past boundary in the when you started with an imaginary So note that the state, once I get a state, it doesn't really matter whether I start with a Euclidean path integral or not. The state is just a state, right? So this is just a mechanism for specifying some ket in the Hilbert space. And once I do that, I can evolve it according to whatever Hamiltonian I want. Let's say the Hamiltonian of the theory that originally I started with, let's say the H that I started with, this was written in, for instance, in Euclidean signature, and let's say I use the same Hamiltonian, but now for a Lorentzian evolution. This is something that I'm allowed to do. Okay, think of the harmonic oscillator again. Harmonic oscillator Hamiltonian, there is nothing in the harmonic oscillator Hamiltonian that tells me that I should only use it for this or this. Okay, so I can use that to evolve it further on. So the claim would be that the initial condition for the universe, according to Hartle and Hawking, is specified by a path integral where there is no path boundary required. So this is what is sometimes called the no boundary wave function. Okay, so that's one statement, and it's quite a race against time. So yeah, and a related fact is that if I wanted to compute the wave function as, let's say, in this form as a wave functional, then this picture, all I have to say is that there is, I am projecting it onto this phi 2, which is basically the same thing as integrating this d phi and with this e to the minus se phi. And because there is no path boundary condition I have to put, I can integrate over everything. Okay, there is no boundary condition I need to put here. That might seem surprising, but it's just the fact that I'm not putting a boundary condition on phi, I am talking about every field configuration that lives in the manifold. That's why there is no particular boundary. This integral is not an integral from some phi to some other phi. It's over all field configurations which are living on this manifold. Okay, so this integral in the sense of it is not starting at some particular phi and going to some other phi, right? So this notation has to be understood in that sense. So if when I write psi phi 2 here, what that means is I'm integrating over the entire manifold, but with the condition that the field configuration on this slice slice is phi 2. So that's what this picture stands for when I specify phi 2 here. Yeah.
How will the t coordinate?
T coordinate. So this is why I said that there is no real need to specify a time direction in Euclidean signature. In Euclidean signature, there is no obvious notion of time, right? There is no negative signature thing. So if you start with the Euclidean theory, there is nothing that really tells you what time is. So what I was saying in this picture was that if you take your Euclidean time direction to correspond to a direction which is, a translation along which is a symmetry of your theory, then it makes sense to equrotate in a convenient way, and that corresponds to some suitable or nice quantizations. But if I want to specify a path integral, I don't need that. I can integrate over all field configurations that I choose to, right? And that's what is happening in Hartle-Hawking proposal. So the idea is that you're basically integrating over all the field configurations where the space-time has only one boundary. So you're taking a t equal to, let's say t equal to 0 is somewhere around the Big Bang, and the wave function at the initial t equal to 0 slice, you're going to specify by integrating over all Euclidean manifolds with all field configurations on them with this particular field configuration that you specified at t equal to 0. So if I don't specify the field configuration at t equal to 0, this is just a ket. That's my initial state of the universe. Okay? So if I specify a field configuration there, it gives me the amplitude for that particular configuration to happen at t equal to 0. So that's what this is. Okay? And I think that's a good place to stop for today.
So for the formation,
Maybe this question. Yeah.
for the formation of this sigma,
Yeah.
Hartle-Hawking said that the boundary, initial boundary didn't factor for the universe, right?
So this is where the state on this is basically your initial wave function of the universe. That's the statement. So and this wave function you can think of as the point of Big Bang, or depending on your imagination. So how do you specify an initial state for the universe? That was what they were asking. So and the claim was that at some initial time, early time in the universe, some t equal to, let's say, some t0, and at that time you specify the state of the universe by integrating over all manifolds, all Euclidean manifolds which have this spatial slice as the boundary. And you integrate over, none of these integrals are doable. That's the great advantage of these proposals. So first of all, in the case of at least free scalar field theory, you can do this integral. But here, this is even more slightly general what they are talking about, because they are also integrating over metric in principle. So here, so far in all the things that I mentioned, I was generally fairly conservative in the sense that you're talking about field theories, standard field theories. But in principle, if you're completely reckless like Hawking is, you can integrate over everything. Okay? So yeah, I think we can stop.